All right. Ken, are you sharing my slides? Okay, great. All right. One sec. Make that bigger. Okay. Well, welcome everyone again to Neurosymbolic Wednesdays. So we have I think, perfect start to the year. Pascal Hitzler, longtime leader in the area. And really pleased we finally aligned schedules. I tried to get him some earlier events. So thank you, Pascal. And it's actually a very good topic, I think, for the beginning of the year. Sort of big picture overview of where AI is, which I think many of us are particularly concerned with now. So, and many accolades, and really one of the original creators of the NESI conference workshop series, now conference. Very lots of leadership in the editorial level. So really providing great foundations for the field, and also lots of contributions in Semantic Web, which I think is going to keep growing in importance. All right. And so while we're waiting for people to stream in, let me just do my usual reminders. So Discord is where the community is. So you have one place to go to discover all the other things. Go to Discord. And you can also watch on LinkedIn. Here are the links. And of course, many of you will be watching through YouTube. And to find out more about ways to communicate, participate in our communities, this link at the bottom. Okay, take your iPhone photo right now. This is all the key information. And then just a reminder of this effort we're starting up, which we hope will really help the community. And for those of you in particular interested in programming languages and systems, please check this out. And so this is a reading group format. So there'll be more than a few minutes discussion at the end. And we generally announce these, in advance, the papers, so you can read them. Now, and this also means that people can present papers that are not their own, in particular, classic papers. And here are some. We're going to have a longer list, and of course, keep extending our list as we go. But here are a few that we sort of thought would be great for someone to present. Of course, in some cases, the original authors might be available. So, but for these classic ones, probably not. All right, so if you're interested in any of these and presenting, please let us know. And as we've been letting people know, we are starting to fund academic research, students and profs. These are some of the topics of interest. And how you get started, you just start hanging out with us generally, and doing stuff with us. And that's how topics emerge. Now, and we are hiring. We are also here to, if you have a Neuro-Symbolic AI startup, we can help you appear, get some visibility by appearing in our meetings. And we're also ecstatic if you want to donate or volunteer somehow. We are a 501c3 nonprofit. All right. With that, let me hand it over to Pascal.
Thanks a lot, Alex, and everybody else. Thanks for having me here. Very excited about that. So I'll be. No, before I start, I need to say that I'm thrilled you're going to start with McCulloch and Pitts. It's a very readable paper, so it's great because there's a lot of history here, of course. All right, but to the talk. So what I'm going to do. This is a non-technical talk, so it's geared towards a kind of less technical audience. There are people interested in AI. So I won't be digging deep. That also means I won't be focusing on whatever technical results coming out of the lab, although we'll touch upon some things as I go ahead. And the broad conceptual perspective is really about trying to find a sober perspective on current AI. And I've talked about this topic a few times, and usually in particular for a general audience. That seems helpful. I told some of the things I prepared here. I explained to my teenage daughter yesterday, and her response after that was, so kind of, why then are so many people scared of AI? And that's kind of the point, right, of where I want to get. I know this is Neurosymbolic Wednesday, and of course, I'm in the neurosymbolic space, and it will come up, but it comes much later, and it will come very naturally much later in what I'm going to talk about. So I'll talk about AI problems and AI limitations. There will be a little bit technical there about overcoming limitations, and then cycle towards neurosymbolic, because that's part of the overcoming theme. For those who don't know me, I'm at Kansas State University, and I've actually been doing neurosymbolic since long time before it was a thing. So there's even a chapter in my dissertation, 2001. And then, of course, there wasn't really much funding available for that theme until recently, but it didn't go away. And I've been a little bit community building at a small scale wasn't possible over the years. And of course, recently, things are bubbling up much more significantly. Most of my funded work during those 25 years I've done in the context of semantic web knowledge graphs is what you would use these days. And of course, that and neurosymbolic go together very well. And again, we'll come across some of these things. All right, now let's talk about AI, and let's take a very bird's eye perspective here. And this is a discussion. I'm borrowing out of Nate Silver's book here, which I really recommend reading. Of course, I'm kind of it's through my own brain. So, but I find this is not scientific, but I think it is a really nice perspective to think about what's going on in AI and around it these days. And what he does is he essentially makes a type of Richter scale for technology disruption. So I call it a Silver scale. That's my name. He didn't do it himself. And essentially, it's a kind of logarithmic scale of kind of how disruptive are certain pieces of technology. And then he makes this list, which you see here on the screen, listed with examples, kind of annual disruptions, order disruptions, microwave, zipper, post-it notes, and so on. Then decennials, every 10 years, things get kind of more invasive in our lives. Social media, mobile phones, air conditioning, credit cards. Big difference here, I think, for me, is that the things listed under annual, microwave, zipper, post-it notes, we would all very well survive without them, and our lives wouldn't really change significantly. We'd have more buttons, right? We'd use the stove more. This is more convenience. With things like mobile phones and social media, without those, our lives would already start looking different. So things are much more invasive here. That's more disruption. Then if you go to the centennial, kind of every 100 years, electricity, vaccines, internet, our lives would be very different. Half of us would probably be dead without vaccines. Without electricity, yes, we would be back to time before that. So that's even more disruptive. Then you can go to millennial, industrial revolution, agriculture. And now you're talking about fundamental change to our lives without these things. And then, of course, you can also go to an epochal ladder, like the Holocene, when humans became the dominant species, kind of earth-spanning disruptions, really, here. And now the interesting thought experiment is, where do you think AI is on this scale? And Nate Silver says it's certainly decennial or, well, lower, right, or more impact. I would also think it's probably already beyond the annual. But now the question is, where is it? And a different question is, where will it be? And it's important to distinguish those two things. And often they are not distinguished in discussions, right? AI is going to so change society. Well, that's a projection. Because right now we may already be on the decennial level, but we're certainly not at the level of electricity. We may get there, but what is actually needed for these changes to happen? And so I want to kind of look a little bit into these types of questions. And you know, the kind of, when people talk about AI, what do they mean? What is AI anyway, right? That is probably the first one we should at least look at and acknowledge that when people talk about AI these days, and they just talk about AI is, and it's often unqualified, and you kind of have to read between the lines what they probably mean. It undoubtedly is a field of research, and it's good to remember that it is 70 plus years old. There is a lot to that. And there have been ups and downs, and they have had much more visibility, the field in society, if you look like in the 80s already, right? But then it's gone down. And the cries for this is going to kind of change the whole world have been out there before. Right? Now, some people, when they say AI, they just mean deep learning, which is kind of the recent technological advance, which drives a lot of what's currently happening. Or even more narrow, I think if you ask more in the kind of general population, what is AI, right? Then they actually think just LLMs, large language models, like ChatGPT and the others, because that's kind of what really bubbled up on the kind of not on the awareness of kind of not non-technical or non-AI business people. You can think of AI as just a set of current technologies. You can talk about AI as a set of future technologies, right? And sometimes it's not clear what people are actually talking about, what they exactly mean, but that really changes the discussion. Sometimes AI means technology that matches or surpasses humans at all levels, right? Which I think we don't have yet. You have people who say, what we currently have is sentient. I think that's an outsider opinion, and I think that's not really defendable. But that's also an opinion we have, right? Perhaps for some, when they say AI, it's just a set of technologies that seem magical because you don't really understand them. Undoubtedly, AI is a social construct. And I'm putting that here not as a cop-out, but essentially because it kind of helps shift the perspective a little bit, that there is more to AI than just technology. And in particular, there are social dynamics and social constraint that actually will also influence future developments and should influence our future projections. And they may be economic, or they may have to do with technology acceptance or risk acceptance in the society. And all of these things will change how the future trajectory of AI turns out, right? And we all kind of are not oracles. All right, one thing I hear, and I want to talk about this because it kind of drives me a bit crazy sometimes, is this thresh phrase, AI has reached PhD level intelligence. And yes, sometimes you find that in papers. What in particular kind of rubs me wrong about that is if this is said without qualification. What do you mean by that? What do you mean by AI? What do you mean by PhD level intelligence? But sometimes it's just used as a buzz phrase. AI has reached PhD level intelligence. If you think this is ridiculous, right? I think so too. But a lot of people don't, right? And in particular, if it's communicated unqualified, then what? No. Kind of, I challenge you to replace your 10 PhD students by large language models and try to continue running an internationally visible research lab. Right? And if you can do that, then we can start talking about whether it has reached PhD level intelligence. I don't think that is going to be there in 10 years, probably not even in 20 years, unless something unexpected happens in the research world. That's my projection anyway. But in any case, right now, you can't do that. So statements like this, without proper qualifications about what is actually meant, are really just overselling, given the current state of technology. Now, if somebody says it will get there, right, then we can start a serious discussion, starting with what do you actually mean by PhD level intelligence? And if you say it's everything a PhD, kind of close to graduating PhD student brings, then I think that's no. Let's look at some AI problems. Let's get it down to earth, right? And you've heard about a lot of that. And it's not about AI splashing, right? There is a lot of things happening. It is disruptive technology. We just have to think about kind of how disruptive is it really going to be. Black people incorrectly judged to be at higher risk to be criminal reoffenders than white people, right? Female names associated more often with family words than career words. All of those are studies, right? And there's you can find them with the information given here. One of my colleagues, Leo Shamir, he does some nice work. One of his work is about galaxy classification from images, I believe elliptic versus spiral or something like that. And what he did was he trained a deep learning system to do that classification on images taken from a certain whatever little piece of the sky, where of course there are always tens of thousands or more millions of these out there with the telescopes you have these days. So what you do is usual, you throw 20% of them away for the moment. You train with the rest of the 80% of the images, which were hand annotated, right? We'll come to the training process later. The system learns how to do that, and you test it with the remaining 20% it hasn't seen before. It does really well on those, and you think, okay, I'm done, right? It can classify galaxies from images. And now it turns out that he now took images coming from a different direction of the sky, and the system didn't perform well. What's going on here? I'll talk a bit more about some of these examples later. Yeah. Police facial recognition technology can't tell Black people apart. Right? I mean, there's variations of this all around. Let me give you something using LLMs. I did that yesterday with ChatGPT. I asked the following. You are in a room with 2 doors and 2 guards. One door leads to freedom and the other leads to death. The guard on the left tells only the truth and the guard on the right tells only lies. What one question should you ask? Implicit, right? You want to survive. And, you know, of course, the guard on the left always tells the truth. So you just ask that guard, which door should I take? Yeah. But that's not what the system gives me. And you know, you may have an idea why it doesn't, yeah? Because this is not the original version of the riddle. The original version of the riddle just says one guard tells always the truth and one guard always tells the lie, but it doesn't tell you which is which. And what ChatGPT does, it gives you a convoluted answer. You ask either guard, which door would the other guard say leads to freedom, right? And then you inverse the answer, which of course is correct, but no, right? You just ask the left guard, yeah? And yeah, kind of, in all of these examples, right, and all of these failures, right, there's always, in essence, the same underlying problem, and I'll come to that, right? Why do these systems do that? This is another one. This is out of my research. We did that for something completely different, but this is part of the investigation. We used an old benchmark, 40 years old benchmark, with very binary gendered family relations. Like Dora is female, has a child Rosanna, and so Luigi is male and has a child Dino and stuff like that. So there's a lot. It's large, right? Or reasonably large, like 40 years ago. And then we also take the information, Dora is a grandmother, Luigi and Maria are not grandmothers. We feed all that to an LLM and ask it to generate a definition of grandmother out of these examples. And the system comes back and does well. It says, well, a female who has a child, which is a person. It takes it out of the examples, not just the 3 examples, right? You give it more, but you get the idea. So that's well, right? Now, interestingly, if we flip the genders in the data we give it. So we don't tell it Dora is female, we tell it Dora is male, and we don't tell it Luigi is male, but Luigi is female, and then ask it to do it, and it gets completely confused. And it gives you the wrong responses, right? Although the problem based on the data we ask it to use is not different, right? But it's getting confused. And of course it's getting confused, right? Because that's how they train, how they learn. They're reverting to the majority perspective, and they can't deal with the differently gendered names, right? Can't do that. And again, I'm going to come back to this example. Now, it's always kind of, in a sense, the same problem. So to understand the problem, let me look a little bit about the more technical side of how you actually train a deep learning system. And for those in the audience who are, technical people and they know this, right? They know a backprop. I'm not going to explain backprop in detail, right? But I'm going to do it this a very, very high level, the mathematical substrate of how learning works. And if you know about this already, then you can just switch off for the next 5 minutes and then come back in. But I want to get everybody there. And not everybody who kind of uses these systems, even trains the system, right, knows what's going on under the hood. And I find that piece rather kind of revealing. And so said my daughter yesterday. All right. So deep learning. And deep learning is also used for doing things like training ChatGPT. A deep learning system is essentially a kind of very crude abstraction of a neural system, like whatever our nervous system, our brain, and so on. So you have neurons, or call them nodes in this case, doesn't matter, and they process information. Now, in this particular case, so in the artificial case, artificial neural network is what the term is, you have them often arranged in layers, in organized layers, make so many things easier. In our brain, that's not the case necessarily. Sometimes it is a little bit. And then you have connections between them, and along these layers, from one layer to the next, and so on, information propagates through these connections. That's essentially the idea. And on the left, there's the input, and on the right, there's the output, right? And since we're talking computers, you're just propagating numbers. The brain is much more complicated, but we're just propagating numbers. And now what happens as you propagate? Of course, you have to encode the input as numbers, like words become numbers, images become large sets of numbers, and so on. And the output again comes as a number, right? And then it has to be reconverted into whatever is important for the case you're looking at. Like, are these two faces the same, right, or not? So that would be 1-0 response. Now, okay, what happens? Like, you take a green node. A green node gets input from a lot of the blue nodes, which are numbers. So the numbers, which are the x's here, it gets these x's, and then each of these connections has a so-called weight attached to it. That's another number, and these usually get multiplied. Something simple. So this w gets multiplied with an x, and so on. X3 gets multiplied with W3, and so on. And then they're all getting into the node where they are all summed up, and then run through a very simple function, which often just does things like squishing the resulting sum into a value between 0 and 1, right? Or something like that, something simple usually. And that's what it does. And that's the propagation through the network. Now, there can be a lot of layers. There can be a lot of neurons, millions, billions of them. But essentially, that's what's happening. So when you train such a system, how do you do that? Well, the first thing is that these weights are something you can kind of set yourself. What you do during the learning is you change these weights. You don't change anything else. You change these weights. That's what you change during learning. You want to find a setting of weights of these many, many numbers, find numeric values for all of these millions or billions sometimes, such that the input-output behavior of the whole network does kind of what you want. How do you know what you want? Well, what you do is you take a lot of examples for which you know what output you want to get, right? Take a lot of examples for which you know what output you want to get. That's your training data. Usually you separate a little bit of this data for testing later and train only on, say, 80% of this data. And then you run all these thousands of input data through the system, and each time you get an output, and you know what you really want as output. So over these thousands of inputs, you can get an average error. How good is the system? Well, what's your weights in this case? Well, initially they're just set randomly, for example, right? And of course the error will be great, right? The average error, but you will get an average error. So what do you do now? How do you do the training? Well, think of it as follows. For each setting of weights, there is a different error, right, which you can in principle compute. Now let me visualize this, and let me visualize this in fewer dimensions. Just two that assume we have only two weights, and I'm doing that because that's what we humans can visualize. And the weights here, take the middle picture, are the x and the y axis. So for each x and y value, you get an error. Now think of the error as the height on this surface in the middle. So if you're on a mountaintop, error is large. If you're in the valley down there, error is small across your training examples. Now, in principle, you can just compute a lot of those and kind of get a rough outline of the surface. But if you have billions, that's too much. You can't do that, billions of weights. So, and of course, that will be a 1 billion dimensional picture, which you can't visualize, but the math is the same. It doesn't really change. So what you do is you take a random setting of the W's, and then you compute the error, and that means you land somewhere here on the surface, but you don't know what the surface looks like. You just know where I stand is the surface, right? I have a certain height, that's the error. And then what you do is you probe with your toe around yourself in all possible dimensions to check where's down. And then when you find out where down is, you take a big step down. That's called gradient descent. And then you do the same there. Again, you land somewhere on the surface, hopefully further down. And then you do the probing again, and you keep going down. And you do that until, well, you're down enough, good enough, right? And then hopefully you'll find a pretty good spot, or perhaps not, because it may be a local down, and there's actually another spot which is much further down, but it's over a hill, so you're not getting there. Of course, there's ways to deal with this technically, but that's generally the idea. You go down, right? You find a deep point where the average error over your training examples is as small as possible. And of course, now you know it's working pretty well over the average of the training examples. There's probably still training examples where it does pretty bad. Can't quite avoid that in most cases. And then, of course, you kind of want to make sure. So you take the training, you take the examples you have not used during training, and you do some testing on those. And then, yeah, if it still works, say roughly 95% of those, then you say, oh, I'm happy. 90% is pretty good, right? And that's it, really. That's deep learning as its mathematical substrate. Now, of course, there's a lot of cleverness going into how do you actually do that for 1 billion of weights, such that you don't have to wait for the training process to finish before you retire. So, yeah, there's a lot of scaling. There's a lot of how do I escape local minima, and so on. Can I take advantage of the layering or train different pieces separately, and so on. So all of that, of course, is possible and helpful, but the mathematical substrate is still the same. All right, so you test on this data, which you had earlier, and then you're 95%, great, right? But who tells you that this still works for data that was not well represented in your input, in your training, and in your testing data? How do you know what actually needs to be represented? And here the problems start. Right? And of course, we can start plugging holes. And if we find out, oops, the system doesn't work for black faces, face recognition, and we know this, right? But we only notice if we actually test on enough black faces. Otherwise, we won't even notice. So how do we do that, right? Oh, did we have enough people who are wearing glasses, right? Or have beards? Did we actually have enough women in there? And then you start plugging the holes, right? Those you become aware of, which in a simple setting, a relatively simple setting, say like face recognition, is probably pretty controllable, although you may still forget outliers like, the person who had a car accident and is currently in the middle of reconstructive facial surgery, or the boxer who got bad beating last night, right, for example, and the system may not work for those. You have to get workarounds for that, right? But that means the system you're dealing with what you have in the data. And you can start plugging the holes. And in a relatively simple setting like this, you may understand where to look for holes. But if you're looking at a very complex scenario, you may not even know where to look for the holes. So, and that's a problem. Yeah. So we'll come back to that. Large language models, it's really the same, right? You get these interesting pictures here, which tell you something about the internal structure of the network. And yes, there is more going on, but the essential substrate is still the same. You train these weights until the input-output function works. Probably more interesting here is what's the input-output function here that you're looking at. And for large language models like ChatGPT, essentially what you learn is the following. You have a phrase which may stop, say, in the middle of the sentence. And then what you want is the next word, right, according to the training data. So you take all the texts you find, yeah, and if you have this sentence, or a sentence close to it, perhaps, then, the words improve, be, and revolution may come a lot as the next word. It's actually tokens, not words. Doesn't matter. We'll simplify here, of course. And then, improve may be the one that comes most often in the training data in these cases. So improve will be the next word. And then it takes the new phrase, including the improve, feeds it through itself again, looks what are the next likely words, the efficiency or patient and so on. And it keeps doing that and constructs the sentences. That's essentially what it does. And it has learned this probability distribution over the possible words out of the textual data, approximately. Right? So they're probabilistic parrots, stochastic parrots. That's kind of what they do. And it's kind of amazing what they do with that. Like, for example, I'm still amazed about the flawless grammar and about the polished rhetorics. But then it's probably also not so surprising that they sometimes just give you nonsense, right? Or weird stuff. Because in the end, what I just explained is all there is to this. All right, so back to the data issues. And something often attributed to, I believe, a statistician, George Box, is the phrase like, all models are wrong, but some are useful. And let me just kind of borrow that and say, all data is skewed, but some data is useful for some things. And what do I mean by a skew? By a skew, I mean, well, if you want to do facial recognition in the US and you don't kind of have data that helps to make your system work well on people with a dark skin tone, then your data is skewed in the sense that you're getting problems, right? For example. In the gender flipping example with the large language model, well, for what we wanted to do, we had a problem because essentially our questioning the system could not override existing gender stereotypes for names. Right. So for us, it was skewed. Was it kind of what is skewed here? Because for other contexts, that may actually not be a problem, perhaps, right? And then for yet completely other problems, it may be a problem because there's a problem with thinking of gender just in a binary way. So, and we're already getting at what is skewed for some situation may not be skewed for another situation. So it depends on what you want to do with the data. What your application context is. Again, narrow application context, right? It's much clearer to make out what's skewed. A very wide application context, like talking with an LLM about anything you may imagine, right? Things may get a little bit more tricky regarding skews. The galaxy classification example. Obviously, there's a skew there, right? Because it didn't work, it didn't transfer. And I believe for a human, it doesn't make a difference. The images look essentially the same, but for some reason, this direction sky or this direction sky, there seems to be a systematic difference which the AI can spot, and we at least don't know yet what it could be. So there's a skew there, probably a skew which may perhaps even be difficult to actually phrase in human terms, but one which kind of makes it difficult for the system. How do I get at that? Right? And I mean, yeah, we found a problem, but in more complex scenarios, you might not even find a problem and just trust the system and get nonsense because the data was skewed in a way which I may not even be able to understand, right? Or even probe for. The liar and truth teller example, the two guards, right? Same thing. The system has seen so many examples of this very famous riddle that it just defaults to that, right? You ask one guard what the other guard would say, and that just overwrites it because that's statistics, right? It's so similar to all of those, and that's what it does. It's just a stochastic parrot. So yeah, and that's where we are essentially, and that's a fundamental problem. You can start plugging holes, but you essentially plug them, one by one, and the ones you're aware of, and that problem is not going away. So narrow AI, that's a term that is being used, refers to AI that's also a specific narrow problem, chest, face recognition, ads matching, protein folding. What is narrow and what not? Of course, that is also in the eye of the beholder, but you get the idea, as opposed to strong AI, which is about broadly applicable or a large range of themes or problems. And if you think of this problem with the training, then essentially detecting relevant skew, relevant for your application, is more problematic the wider the application space. You can detect and fix skews, right? the narrower your problem is, the more you understand the space. It's the human who understands the space. And I believe some of that may be going on all the time, because the problems, some LLMs which I can use on the web, the problems they had a few months ago, they no longer have now, after it kind of the problem rolled through social media. So somebody's fixing this in some way. And it's not the AI that's fixing this. It's humans who prompt the AI to fix it in some way. So detecting and fixing skews is also something that involves a lot of non-AI methods, right? So, it's PhD level intelligence? No, I don't think so, right? All right, so I talked about some of this already. What is data skew? And really, it depends. It depends on the person, it depends on the application. What do you want to use it for? And that brings us to the other problem. Kind of, if we use training data, then we somehow assume that the data is correct. And what does that mean? What is ground truth fundamentally? And let's just make a simple example. What is the population of Kansas City? And we may even say, well, if I ask that question, there is probably some ground truth there. I say probably. I'm going to come to that. The first question is kind of, it's changing all the time. People get born, people move away or move in, and so on. So it changes all the time. What do I mean? Well, okay, let's change. What is the population of Kansas City now? And still then, what is the ground truth here? Kind of, there's a baby being born right now, right? It's how far does it have to be out of the birth canal to count as part of the population of Kansas City? When does somebody move away? When they kind of locked their door for the last time? Well, they may notice they forgot something and come back an hour later, right? So do we need to be able to predict the future to assess the population of Kansas City? And in any case, nobody's counting. This is all statistics. Different statistic models to assess, or based on different polling of people will give you different reasons. So, if there is a ground truth, it's elusive. Yeah. And well, does it care? Well, for a lot of cases, it probably doesn't matter. For a lot of application cases where you need to know the population of Kansas City, right? But I'm taking this as an example because this is a very simple example. And a lot of other examples are much more difficult. And truth, essentially, is a social consensus. In a lot of cases, at least. Let me hedge that a bit. But, in the end, truth is a social consensus, most of it anyway. In the same vein, there was a really nice presentation by two digital historians from Michigan State at the US CTS conference just 4 weeks ago or so, Dean Rayburn and Walter Hawthorne. They're historians, digital historians. And they talked about difficulties they have with using kind of whatever LLMs for X. And one of the things they said is multi-perspectivity is central for history. Multi-perspectivity. And that means different opinions discussing and clashing and talking with each other. And that is so counter to the idea that you have ground truth data that you use for training your system. And what you get is something that can generally solve all kinds of problems, right? That's just not compatible. All right, so, and this really asks the question, how far can training with more data plus plugging skews really carry? Fundamentally, and probably not to PhD level intelligence, right? That's my thinking anyway. Still, makes sense, in particular in narrow AI contexts. We're broadening what narrow means right now, perhaps. Yeah, but still, that's where we are. It also prompts the question: can we do something smarter than just throwing more data at the system and plugging the problems which we become aware of? And that brings me to the next theme. And no, it's not neurosymbolic yet, because neurosymbolic isn't the answer to this. Let's think about this first from a human AI teaming perspective. Has a really nice paper in Nature Human Behavior, and this and the next slide are out of that paper, really. Recommend it for reading. By the way, I shared the slides with the organizers, so if somebody wants to look up the references, then they should be obtainable, or from me. All right, so this Nature paper, they did a meta-analysis, comparison between human AI teams, human alone, AI alone. What is better? And there's some LLMs in there, but it's January 2023. One of the things I don't like about the paper is they never really say what type of systems are in their data. They just talk about AI systems. So apply with caution, right? Like all this. And it's a statistical meta-analysis. So there's limitations to what you can read out of this. But out of this analysis, two things, there's a lot, it's a really rich paper, but two things that come out of that is the following. Statistically, if the AI is better than the human, then the human AI team is often worse than the AI alone, right? But also, if the human is better than the AI, then the human AI team is better than the human alone and better than the AI alone. Again, statistically, so whatever, majority of the cases with statistical significance. That's interesting, right? The problem, of course, is that we do not know upfront whether the human or the AI is better in all cases, right? So whom should we trust more? Essentially, what this tells us is that if the AI is better than the human, then the human tends to mess it up even more. But at the same time, if the human is better than the AI, then the human will probably correct for the errors, right? And that's my experience, right? I asked ChatGPT to write a cover letter for me, and then I can go over the cover letter and I can remove the problems, fix them very quickly because I understand what the cover letter is about. And the result of that is that I get something that is in contents correct, has a rhetorics, a level of language I'm unable to produce, and flawless grammar, which I'm also unable to produce in most cases. So that's great, yeah. But if I ask it to do something, write a letter about something I have no idea about, then the more corrections I make afterwards, the more I'm probably going to mess it up even further. That's kind of my example for this. So how to design human AI teaming to maximize performance, right? And things like give only the subtask to the AI where the AI is clearly better than the human. Let the more capable partner decide on task allocation. The process is decisive. And in a lot of cases, that may perhaps be the smarter way of doing that. And that's what we're doing already. That's actually happening a lot. And I'm going to come to that without us being much conscious about it in a sense. All right. Just 1 second. Thank you. This is from a different paper in Nature Machine Intelligence. Part of that paper is a little bit of a listing of things where humans are better than machine learning usually. And these are things like generalizing from a few examples, divide and conquer approaches, excelling at compositionality, generalizing towards noise, meaning shifts, out of distribution data, right? Like a different guard riddle, which may not be in the system. And let me add some things not in the paper, but which I would also add, if there's specific deep or niche expertise that the human has, then it may actually do better than the AI. Multi-perspectivity, we talked about that, taking broader context into account, understanding when to deviate or make an exception from mainstream opinion or lines of thought and things like that. Humans are good at that, or relatively good at that. And kind of what we do when you interact with systems, then that's often what happens in situations where AI really is helpful. Like I mentioned already, LLM language editing assistance, right? Or say automated driving assistance in the car. The human is still needed. The human does the checking. The human does the quality control and the exceptions and so on. That's where we are right now, right? AI agent call center, yeah, can do the straightforward, easy frequent sims, get a human for everything else if it gets stuck. That's what happens. Cell phone assistant, yeah, you're a cell phone assistant if you use it. You're the backup, yeah, if things don't work. Things can easily go wrong if you take the human out of the loop. And that's the state of the art. That's where we are right now, right? And how optimistic are we to get around it. Let me add another type of limitations. So this is a little bit of a change of tune now. Things that deep learning systems are not good for, right? Or they're not good for if they're needed in some application context. Like, for example, we cannot easily check on their assumptions. An LLM kind of, why does it give me the responses it gives me? I have an example on that later, right? The assumptions on which it bases its reasoning and its response are implicit in millions of learned weights that are somewhere in this neural network, and we cannot read it off. There's research going on, part of that is ours. To what extent that will work, we don't know, because it's kind of, it's just these weights. And there's no meaning to this for us, or not a lot of it anyway at this stage. We cannot check on the reasoning, right? Why are you classifying this galaxy as spiral? Yeah. And yes, research is working on partial answers to that. Yeah, but it's partial answers. They're not really good at these systems. And a lot of these kind of understanding these answers had actually nothing to do with deep learning. It's other methods. We cannot force them to be precise in their reasoning, right? Like saying, okay, assume Dora is male. And it just gets overruled in a lot of cases by their defaults, right? Be stereotypes, which they have, or call them prototypes or whatever you may want to call them, or biases, right? Generalization through learning requires imprecision, and that's been known for a long time, right? And some people call this the no free lunch theorem. It's a trade-off which fundamentally you can't change. Of course, you can plug holes. We cannot make hard, specific assumptions, right? Like assume Peter is the mother of Alex, talked about that already. So deep learning systems are essentially black boxes. They're still black boxes. We're trying to look inside, understand what's going on, but this is only starting. And to what extent that will really work is a different question, right? You just have to trust what they're saying or double check on it. And that's essentially where we are. All right. So now with these things, with these specific things I just mentioned, right? Humans are sometimes reasonably good with these if they have the expertise, but humans are not good at these at scale. That's a problem, right? Wouldn't it be nice if you had something that could really excel with respect to these aspects and perhaps add that to the AI machine learning-based deep learning experience? And it turns out we do. We have systems. In fact, we have AI systems that are really good at those. And they've been around for a long time, right? And that brings me to Neurosymbolic. So Neurosymbolic is not the cure-all, but in these specific aspects, which I believe are important for a lot of application scenarios, it can help. So what is symbolic AI? And that's where Neurosymbolic comes from. Neuro is the deep learning or artificial neural network side of things. Symbolic is the other type of AI thing. Symbolic AI, probably the original form of AI 70 years ago. The idea here is that knowledge is encoded in formal logic. So not in just, learned and then somewhere in the weights, but it's encoded in formal logic, which is actually in principle, at least readable for humans. It's coded and not learned. And knowledge graphs are part of that. Ontologies, more generally knowledge bases are used here. And these knowledge bases, they can have facts like Mary is a child of Jane, Peter is a parent of Jane, stuff like that. They can have rules like if X is a child of Y, then Y is a parent of X, or if X is a parent of Y and Y is a parent of Z, then X is a grandparent of Z, and there's variables in here, right? So that's universal rules. And then we have algorithms, and sometimes they're very complicated algorithms because their logics can get very complicated. Algorithms which can do reasoning, like taking these two facts and two rules above and derive from it with mathematical precision that Jane is a grandparent of Mary, right? And you can do that for much larger things. There is a scale problem sometimes, but that's what happens there. And this can be done with mathematical precision, mathematical correctness. There's provable correctness here that what you get as the output, Jane is a grandparent of Mary, is provably correct with respect to the assumptions you have explicitly made and can inspect. Plus, you can inspect the reasoning chain if you want yourself or automatically. Of course, it may be long, right? But in principle, you can, and you can understand each reasoning chain in the reasoning and understand what's going on there and verify if you want to. We cannot do that with an artificial neural network. So there's no statistics involved in symbolic AI. We have provable correctness, we have transparent assumptions and inference rules, we have traceable, understandable reasoning, traceable, understandable for humans at least. In principle, there may be a scale problem, sometimes for which we need good tools. And that's symbolic AI. right? And that has the ability to do these things we talked about earlier. Let me go back, right? Checking on assumptions, checking on reasoning, precision in reasoning, making hard specific assumptions, even if they go against common sense. Hypotheticals, counterfactuals, all the things machine learning systems have trouble with, right? All right, so let me give you an example, another example here. Going back to the family relations thing, right, where the gender flipping made a problem. And this is just the same slide as earlier, right? So gender flipping made a problem. So how can we solve this using a neurosymbolic approach, right? So these are two different systems. Just stick with the top, GPT-4o. If we ask the original system, it does really well on the 9 examples in the benchmark. It's a 40-year-old benchmark, so there's not a ton of examples here. But if we flip the genders, it gets confused about half the cases. Yeah. So now what can you do now? And the point is now that we can use a symbolic system to check on the solution. We use a symbolic reasoner, symbolic AI system that doesn't make mistakes. Yeah, it gets the solution from the system. It checks whether the solution is really a solution. If it's not, it sends it back to the system, to the LLM, with an error report and asks it to do again. And if we do this just 3 times the loop, then we improve from 4 incorrect to 2 incorrect, right? And we could keep going. Now, what's the point there? Because of course we can solve the original problem using a symbolic system as well, right? Well, the point here is that just checking on a solution takes much less time in terms of computation time than using a symbolic system to produce the solution in the first place. So essentially what we're doing is we're making a team where the symbolic reasoner is there to give us accuracy, and the LLM system is there to give us speed, things they're both good at, with a win-win situation. This is very similar to the human AI teaming situation, right? You just kind of need to do it the right way. And now we're in the middle of kind of neurosymbolic ideas, or at least one neurosymbolic idea, right, where you have a neural and a hybrid, the neural and the symbolic system which team up. And you want to do that, for example, in such a way that the neural system can do the learning. It may only have statistical correctness, right, black box. It may be very quick, right, once you have it trained. Training takes time, but once you have it trained, they're usually pretty quick. The symbolic system, right, is bad at learning from data. There's no good algorithms for this, really. Of course, people have tried. In some situations it works, but it's tricky. They're also expensive to develop. But they are transparent, verifiable, explainable, so they can do the checking, for example, in the case we did. So bring complementary strengths together, and that's the idea of neurosymbolic. All right, neurosymbolic is not new. I mentioned that already. We ran the Neurosymbolic Learning and Reasoning workshop since 2005. Since 2024, it's a conference. And of course, during much of this time, it was, well, not a topic that had a lot of following. Although, you know, I rarely met a person who didn't think it's important. It wasn't the time, right? So a small community kept it alive, and now it's growing again, of course. As you all know, we're here at Neurosymbolic Wednesday. There's some recent overview of articles that are highly visible. We also have a community Slack with over 1,300 people. If you want to be on it, send me an email. You find my email easily online, and I'll sign you up. We don't share the sign up link publicly because we don't want spammers there. So if you prefer Slack over Discord or use both, right, then you can use that. There's books, some of them going back a long time. Yeah. One thing I want to notice, though, is that this hybrid idea is only one idea, how to get the neural and the symbolic together. And of course, it's an active research community which has quite some history. And by the way, if you go read the McCulloch and Pitts paper in the reading group, that is a neurosymbolic paper, right? 1943. It's probably one of the first neurosymbolic papers, essentially. Of course, they don't use the term. So you can go hybrid. You can also try to realize formal logic reasoning in a deep learning system, for example. That's tricky. We've done some research there. You can try represent symbolic knowledge within a neural system rather than in a logical system or a knowledge graph, or do some conversions back and forth if you manage. You can use high quality symbolic knowledge bases as inputs to your system, right? And then you're looking at graph rag type of systems. That's really neurosymbolic. Or use symbolic methods to understand, represent assumptions or reasoning processes and so on. There's a lot of different possibilities how to bring things together. I'll skip over the next one, which was about reasoning. Doing symbolic reasoning with neural networks, it's hard. I'm not going to go into detail. I want to talk about explainability, because one of the things is about understanding the assumptions underlying the reasoning, or the assumptions under the factual assumptions underlying the output you get from a system. And as I said, these things are implicit in a neural network because they are somewhere in the weights, but we can't read them off. And then, one cop out may be here to say, well, if I work with an LLM, I could just ask it, explain to me how you come to this. And this is such a no-go if you think of how these things work, because the LLM does not have any insight into its inner workings, right? Or at least not really. Let me just give you, again, something I stumbled into yesterday. And this is, again, the modified GARDS scenario with the liar and the truth teller. You know who is what, right? Then I asked the system, why do you give me this answer? And it says, well, this is a classic logic puzzle, so that's why I give you the answer. There isn't much introspection here, right? I'm kind of, I want a little bit more, right? Now, frankly, humans kind of post-construct their answers as well. There's a really good book, The Righteous Mind, which I recommend here, right? But the problem arising out of the human reconstructing the answer and then interacting with me and the AI doing that are really different. Let's move on with the example. So after, why do you give me the answer? I keep asking, are you certain that this is why you gave me that answer? At this point, the human would stop and think, right? The system tells me, yes, I'm certain, and it gives me a long explanation why the answer is still the right one. And then I ask, could you give me a different answer that is still correct? Yes. And then it says, yeah, you can ask other questions. All of the ones it now lists still involve both guards and are also a solution to the original riddle, right? With a human, I can enter into a meaningful level discussion, right? Or do a meaningful joint exploration of the problem space. With the LLM, I cannot. This is not PhD level intelligence, right? Now, once I get to the point that I'm kind of getting fed up and ask, could you just ask the guard on the left directly? Now notice, I know the solution, right? So I'm prompting it, putting its nose to it, and it tells me, yeah, you can certainly do that, but you will not get a solution that way. So it still insists on this. And then I go the next step, and then, and I believe this is scripted. I say, I think you're just wrong about this. And I think here something happens that they kind of either programmed into the system or, fine-tuned the system such that it responds to questions that are like this, where the user says, you're wrong, right? And then it starts to reflect, yeah? There was a skew that was plugged, so to say, right? And now if I do that, then it kind of comes up with the insight that there is a much simpler solution and so on. Now, note I can get there, but only if I already know the answer. So really asking the system to explain itself, well, you may be lucky and it gives you a good answer, right? Or you may not, but you better be able to look at that. By the way, here is just for the fun of it. I believe I have 5 more minutes. If that's not correct, then please let me know in the private chat. But I believe that's kind of roughly what I should have. Or if I have a little bit more, let me know as well. I have a few more slides I can use, but don't have to. All right. So this is a modification of the guard puzzle I asked. And here I say the guard on the left only lies and the guard on the right never tells the truth. What one question should you ask? Now notice that both always lie. So essentially what you do is you ask one of them, right? And then you do the inverse of what they say. Yeah. It gets completely kind of, it's interesting what it does. What the system does here, it notices that I kind of twisted it. And it gives us the correct analysis of how I twisted it, finds out both guards always lie, and comes to the conclusion that I have no way to find the correct door. Okay, it's a stochastic parrot. It's a probabilistic parrot. Be careful, right? What you get. Now, of course, the solution is you just ask any of them and just do the opposite. All right. So I want to tag on a little bit of neurosymbolic work we do regarding explainability. And it really has to do with, can we trace the inner workings of an artificial neural network? And kind of how would you even start that? Because in there's just all these weights, right? You try to find structure in these weights. And the inspiration here, the general inspiration, is from what brain scientists have been done for a long time, and even more since MRIs have been around. They find that certain pieces of the brain, sometimes even small sets of neurons or individual neurons, actually seem to represent something. Jennifer Aniston neuron, I think, is a buzz phrase around this topic, right? So there's this kind of human homunculus where you can say, okay, this part of the brain is your thumb, right? Physical representation of the thumb. Can we do something similar for artificial neural networks? Of course, there is no brain and no genetics, right? So if we find a specific region for one network, that won't be the same area in another network, right? But if we can do it for one, that may already help us understanding what's going on. What does it internally detect, and what may be a reasoning chain through the different layers. Now, this is tricky work, to be honest, but that's what we're doing. And yes, we have been able to make some first inroads. How far they will carry, I don't know. And there's still uncertainty here, of course, right? But it may help make things better. It's not going to fix the problems, right? So one of the things we've done is we looked at LLMs and looked for a scenario where they're flawless, right? Where they're just, you don't spot problems. And that's with grammar. Their grammar is just flawless, at least as far as I'm concerned, in English. What we've been able to do in an LLM was to isolate relatively small sets of neurons out of these billions there, relatively small sets of neurons to represent simple grammar categories, such as verb and noun, right? We want to go deeper there, of course. But, so it seems that it's possible, right? And we can say, okay, it has found, now, next thing is a verb phrase or things like that. Is that directly helpful? Well, probably not. But if we can carry that over to semantics, to meaning, which is, of course, much more tricky because A, they make mistakes, and B, there's much more categories which are much more kind of shady and unclear, right? Then of course, we can start looking at how does the reasoning perhaps work over the layers, right? But we have some, at least an archive paper on the grammar thing. So that's an inroad. We have more mature work on this line of thinking. I was told I can have a few more minutes, so this is the last thing really I want to talk about. We have done something similar for a deep learning system that does image classification into scenes. And for those who know about the technical content, we were looking at the dense layer, essentially, which only had 64 neurons in this case. We're using 8020K as our benchmark data set for this, because the images have annotations. Anyway, I don't want to go into detail here. But what we're doing is we're using a symbolic system, a concept induction system, which actually can do things similar to the LLM gender thing we talked about earlier, to find out what are things on the images abstracted, that's how I use the concept induction, abstracted, that make a certain neuron or a small set of neurons in the dense layer light up, right? And for this analysis, we use actually background knowledge that consists of about 2 million different nodes. It's actually just a class hierarchy. But that actually works pretty well and in a lot of different scenarios already. And again, there's more work we can look at. But just to give you an example, we found we have images in the 8020K data set. Then we train a system to do scene classification. And then we look at a specific neuron. After training, we look at a specific neuron. And there's images which light up the neuron, images which do not light up the neuron. Then we run this through our concept induction analysis. And the concept induction analysis may tell us, well, similarity is that a lot of these positive images have crosswalks. A lot of negative images don't have crosswalks. And crosswalk may come from the labels, or it may come from the background knowledge to which we link the labels. Doesn't matter. But then we have a hypothesis that crosswalks may make neuron 1 fire up. Then we test that with new images, actually from a different data set. And if we run through this, then out of the 64 neurons in the dense layer, we can confirm, I believe, 19 that they react to specific things on the input picture. And notice we feed only the images to the system and not the annotations. So no words going in there, no labels, just the images. Of course, neuron 1 also reacts to other things, right? So we're still working into that and through that, but this is a very strong thing. So this is statistical significance is really strong here. So, you know, if we don't use concept induction but use an LLM to do the analysis out of the labels, then we get also responses, but not as many of them we can actually confirm. So the symbolic system does better than the LLM in this case. But then we have other research, and I'm not going to do details here, that shows that the LLM produced categories make more sense to humans than the concept induction induced categories. So there's again a trade-off, right? They're good at different things. So still working through all that, and there's a whole trail of papers here. But I'll stop that here, right? This is also neurosymbolic work, but it's a neurosymbolic analysis of what's going on inside neural networks, with the hope that sooner or later that will actually help to find problems more easily. All right, so back to the silver scale. Where is AI really? Where is it right now? Right? And yeah, it may be at the decennial. I really don't think with kind of the examples you see and so on. You know, does anybody still want to argue it is in the centennial column already? Where will it be? And you know, I don't think we'll get rid of the skew problem. We can do narrow AI, yes. And I believe that a lot of the commercial applications of LLMs, right, they will have to do with narrowing an LLM down to a narrow purpose, and then you have a specialist system that is good on that. And yeah, for that you can start plugging the holes, right? There will still be holes, there will always be holes, but having something that is much more generic is difficult, right? But then there's another piece to that. How disruptive the technology will be also depends on other things. Like, for example, one of the things Nate Silver lists here as millennial is the atomic bomb. I find that rather difficult. Would my life be so different without the atomic bomb? I'm not so sure, right? Was the atomic bomb really disruptive? Well, the point is it could have been. You know, I believe there is an argument to be made that at least twice, you know, over the Cold War period, we were pretty close to a global nuclear war. That would have been disruptive, right? But we didn't get there. So I'm not sure the atomic bomb is under millennial. Is nuclear engineering, nuclear technology under millennial? I'm not so sure, right? And if we make so much nuclear waste that in whatever 100,000 years, our descendants will have a problem with too much nuclear waste, right? And they may have an opinion about this. But you know, right now, I don't know if it's at the order of magnitude of the Industrial Revolution, right? But of course, if humans had done things differently, the atomic bomb may very well be in the millennial row, or probably even worse, because it may be the end of life as we know it. And what that means is that it's not the atomic bomb itself, it's what we do with it. Or it's not the nuclear energy itself or nuclear technology, it's what we do with it. And there may be something similar with AI. What are we going to do with it? Are we going to just make completely autonomous atomic bombs and let them do whatever comes out of their probabilistic algorithm? Now that's perhaps really dangerous. And there's other scenarios which can be really dangerous on a kind of all human scale. And there's of course a lot of things that can be dangerous on a smaller scale, right? But what is society going to say about that? What is the accepted risk that an autonomous car would drive you into an accident where you die? What is the societal accepted risk? And people may differ about this. And some people may say, well, if that means 1 out of 100,000 dies, while right now 1 out of 1,000 dies because humans are just bad drivers, then that's acceptable. And others may say, no, it's not acceptable for me, right? I want to drive myself. So, and here a question is, what's going to happen there, right? So how to do that is a matter of policy, is a matter of remaining level-headed as an academic and as a technologist and as a business person in terms of, being realistic about the risks and about the promises and what it means. And that's what we all, I believe, have strived for. All right. I stop it here. Thank you very much. And if there's any questions, then please ask now or later. Also, feel free to follow up, sending emails, etc. Very happy to do that. Or on the Slack, of course. I'm just a Slack message away there.
Right. Thanks so much, Pascal. So, yes, I'm really, this might be the best we've had yet as far as, because I always feel, especially with people who are not working in AI research, I have to start from the beginning where you did. Like, okay, let's first understand what LMs really are, and so on. So, I think you did a fantastic job of that, and you raised a lot of great points. So I have a few questions. Olga, you may have some questions, but let's start with the audience.
Yeah, we'll have some questions from audience. The first one, I'm not sure if it is very clear, but the question is, 1 second. In your mind, what's the difference between assumption and guessing? I believe it's related to something you mentioned maybe in the middle of your talk. Do you understand?
Sorry, ask the question. The difference between assumption and
guessing? Just guess?
Okay. Yeah. Yeah, so I'm not sure if my answer will actually fit the intention of the person asking the question, but let me try. So what I mean by assumption in this context is essentially an assumption based on which I act or derive a consequence, things like that. That's an assumption, right? So essentially an assumption is kind of, what do I think is the case, right, in reality, which causes me to act. Like, for example, yesterday evening, I had the assumption, I assumed it to be true that today at 11 a.m. local time, I would have this presentation with Centauri AI Institute. And based on that assumption, I set my alarm clock, right? So, and that's technically what's meant with assumption in this case. And I know the natural language word can have different meanings, and apologies for not making that clear, that I meant this more technical meaning, which comes more out of the logic and symbolic AI community. So that was meant there, right? Well, guessing is I don't know, I'm just guessing, or I have a gut feeling, right? I may have a probabilistic assessment and guess based on that, right? And so on. So that's the difference. And I meant this in the more technical sense here. But thanks for asking for the clarification here.
Mm-hmm. Thank you for that. The next question is Neuro-Symbolic AI implemented in an existing AI?
Okay, I could talk for half an hour about this, I think. Well, let me say yes and no, right? I think that a lot of the AI systems we use, application systems, have symbolic components. Often, I believe, without the people developing the AI really being aware of it. Right? It depends on how exactly you mean the question. Right? Now, the point is that there is not one approach to neurosymbolic AI, and where the community research is right now, the research and also people trying to get it into practice, is more in the kind of, how do we approach this, right? In the framing of my presentation, how do we chop the problem into, say, sub-problems, right? And then have the right AI approach or non-AI approach sometimes to solve which subproblems such that we can fiddle them together and solve the bigger problem we have. And yet it has been done. And there, some systems which I still think are feasibility systems, right? Which go a certain way of kind of helping you along with that, right? Like, for example, if you talk about GraphRag, for example, right? I mean, there's tools out there which help you do GraphRag. That's Neuro-Symbolic, yeah, for example. So that would help. But that by itself doesn't solve the problem for you, right? You still have to have the right graph, right? And all these kind of things. And then, see what can that really do for you or not. And there's others, like, somebody made a plugin for Prolog that can query a neural network as an input to a Prolog program. Prolog is kind of quintessential symbolic AI in a sense, right? And so on. So yeah, there are systems around which can do pieces. But if you're a practitioner or more interested in applications, say, can you give me something to play around with? I think then right now the answer is not really, right? You need to work with a researcher or with somebody who does technology applications. And to be entirely honest, sometimes I get these questions, right? I would like to know, how I can use AI effectively in the context of human resources in my company, right? And kind of, can you advise on that? And then generally I say, at this stage, if you don't know what you're doing, just don't do it, right? And I think with Neuro-Symbolic, that's similar, yeah. So yeah, ask somebody and work with somebody who knows what they're doing. Sorry for that answer in a sense.
Thank you. Okay, the next question is, if ground truth and social meaning themselves drift over time, how do we distinguish ordinary data drift from a deeper semantic or normative drift?
I haven't thought about this. It seems to me like that is a question that borders on the philosophical. And so there's probably a lot of answers here. My first line gut response, would be, I'm not sure this is fundamentally different, right? In the end, the question is, what is correct? And what is correct changes. And there can be a lot of reasons why what is correct changes, right? And what is correct can just change because something gets outdated for all kinds of reasons, right? And if you don't have a timestamp on your data, you don't know, yeah? Things can get outdated because opinions shift, because definitions shift, because a social consensus shifts. The truth, what is correct, can change because you ask somebody else or you work in a different context. And I think fundamentally, I would think these are pretty much the same, but I'm very sure there's people who have much better opinions about this. Is it possible to look at specific problems related to that and fix them in a technical way? And then the answer is yes, of course, right? I mean, the first thing is put timestamps on your data, right? For example, put provenance on your data, right? When you make a model, be it a statistical or an AI or whatever model, right? Be explicit about your assumptions. Be explicit about what it does and what it doesn't do, what you have tested it for, what data you have used, all these kind of things. All transparency helps, right? So we can do that, right? Yeah, I think that's where I am at this with the limited knowledge I have.
Mm-hmm. Thank you. The next question might be related. Given that current models optimize for statistical correctness rather than communicative force or social consequence, are we even evaluating the right notion of correctness when we talk about drift?
Yeah, and I think no. The answer is no, we don't, right? We do what we can technically. Now, is that a problem necessarily, right? And I don't think it's necessarily a problem. The problem, I think, occurs when technical people coming out of certain contexts do this stuff without being aware that doing it this way is problematic, right? You need to be aware of the limitations of what you do and deal responsibly with these limitations. And I know that's a problem, right? Because you're in a company context and you need to sell your stuff, right? Even coming out of the research context, this is difficult because it's difficult to get research funding without at least doing some overselling of what you do, right? So it's often difficult to get a paper published without doing some overselling of what you do and hoping the reviewers don't pick up on it, right? So, and now we're getting into ethical questions, right? And where's the borderline between right and wrong? So it is problematic, absolutely, yes. It's also very, very difficult. There's a really nice book I'm halfway through, which is called Critical Theory of AI. It is somewhere linked earlier, right? I really recommend that because it gives you a broader perspective on kind of the whole social context around this social construct in this AI. Awareness is important. Awareness, telling people about it, making sure people. Like my daughter said, right? Why do people think this is scary, right? And part of my response was, well, technically it may not be scary, but the question is still, what will we do with this power at our fingertips? And scariness may come in that way, right? So, yes.
Okay, thank you. The next question is, what do you think of LeCun's world model idea?
Foundation models are all the rage right now. Yeah. We have to try, right? I mean, if anybody would have said 15 years ago, essentially you're just taking some deep learning architecture. They were around back then. The ideas are actually much older, right? The ideas have been around 30 years ago for deep learning. Yeah. It's just the computers weren't quick enough. Yeah. And then of course, you need some tweaking with the algorithms to make them scale, right? But that's not a fundamental breakthrough. That's engineering. So if somebody had said 15 years ago, with this approach, you get something like an LLM that does flawless grammar and really, really polished English language. And this is cool, right? Most AI researchers would have said no, right? Grammar is a problem, right? Now, of course, we still have a problem with content, yeah? And I don't think that will really fundamentally go away, yeah? And then there's the no free lunch theorem, which I mentioned, yeah? And essentially what it says, and I'm simplifying, of course, is the broader a problem you will try to solve, the more the system which you set up will suck in some specific aspects. That's essentially, in some words, the no free lunch assumption, right? Theory, they call it a theorem. It's not a theorem. It's an assumption in terms of different assumptions, in terms of guessing, right? Or informed guessing by people who know about this. So we have to try. We have to try how far we can push this. Of course, we have to try, right? As researchers, we have to try. As a society, I'm not so sure we have to try, right? But the way society ticks right now, we probably have to try as a society. That's just how our social dynamics is. So go ahead, show me how well it works. Yeah, I'm skeptical about how far LLMs alone will carry, right? So I'm also skeptical about how far this alone will carry. I believe in order to get to real world model strength, to PhD level intelligence, to these kind of things, we need breakthroughs we do not see yet. Idea breakthroughs, real breakthroughs, like whatever, somebody like Einstein coming up with relativity theory, and they're not on the horizon, and it's very difficult to say how long they will take, right? And I'm pretty sure I will retire before I see all that. I'm probably going to die before I see PhD level intelligence, right? But now I'm guessing, not assuming.
Okay. Thank you, Pascal.
Even with humans, human PhD students, you don't always have PhD level intelligence. So.
I did not want to start on that rabbit hole, right? Because of course, I mean, and this is the counter argument to all that, right? Now, I think you're raising a really, really important point, Alex. So let me talk about that. Of course, where do these assumptions come from, right? Kind of that we're on the road towards human level intelligence. And one of the ways how you can get at this is by saying, well, in the end, we are just machines, right? I mean, of course, not based on artificial neural networks, but based on natural neural networks, right? And we are just machines. If you take that as an assumption, then, at some stage, consciousness, sentience, and, PhD level intelligence just emerges. Out of, you've built a machine that's complex enough such that it emerges, right? And I can completely see that line of argument, but A, it's a guess, and B, we have no clue what level of complexity we need to achieve to get that, and we have no idea what timeline that will happen. So yeah.
We're near the end. Maybe let's squeeze in one LinkedIn question, Olga, and then I'll ask a question.
Okay, sure. So you pointed out the need for a protocol for neurosymbolic agentic or something like that. Isn't the theory of agents and multi-agent systems a starting point rather than reinventing all the contributions made for over 3 decades?
Yeah, things come back with new words, right? And of course, multi-agent system, when I kind of started to be on the computer science scene 25 years ago, multi-agent systems were a thing. Actually, hybrid systems was a thing, right? And then it went away, yeah. And now it comes back, with under a new term, right? Actually, agentic is back, right? What was once called linked data came back as knowledge graphs with some modifications. That's computer science for you, right? And of course, this is good and bad, right? And the good thing here is that other things have moved on, our understanding has moved on, so things come around and we can build on the earlier insights. Regretfully, what happens is that a lot of the earlier insights are often lost, right? I think, it would help to sometimes read up on the old neurosymbolic stuff, because it kind of tells you kind of what doesn't work, because we tried. And so the answer here is yes, right? The problem here is, of course, right, kind of, is it fair to ask young researchers to work through, I don't know, 20 years of literature that is obscure, and difficult to find, particularly if you have no idea how things were phrased back then and so on. And it's nice, but can we expect that? So it's up to us, right? It's up to me to find a platform to inform about. There's a history to neurosymbolic, right? Because I've been there before. And so, the answer is yes, I think there's a lot of insights to be had, right? But we have trouble, keeping up with the frantic pace of publications in any subfield of AI right now. It's really tough, right? We'll have to do our best. Yeah, and that's just how the reality looks like.
This is part of the tough job we've decided to try to take on here at the Institute with help from leaders like yourself, Pascal. Quick, there's many things I want to ask you about and comment on, so we'll have to have you another time, have you back. But one quick thing, sort of one of the themes and things you discussed is how slippery even some of the foundational idea or concepts are, like ground truth. And another one is, to me, is when you're talking about trying to figure out if a neuron in an artificial neural network is symbolic in nature or not. Does it, this ties to many things. Neuroscience, the grandmother cell / Jennifer Aniston cell, as you mentioned, and even in neuroscience, there's some, it's not agreed upon, right? So many people, arguably most in neuroscience, believe in this distributed hypothesis. But there's some evidence of, the grandmother cell also. And even in artificial neural nets, it's a bit mixed. I think most people, or many people, sort of really believe, no, a concept must be distributed, must be a vector. But then again, the output of, say, an image classification thing is a symbolic output. And so it seems a bit mixed even. Another mixed thing is, like you said, humans, one thing I find frustrating is trying to convince people that the explanations given by an LLM are not real explanations, because, and this is why we have this idea of mechanistic interpretability. But then again, as you said, humans maybe don't even do that properly, so they don't understand their own mechanism. So, but I think, and McCulloch-Pitts came up, and McCulloch-Pitts is, to my knowledge, the very first neural net, and it is symbolic in was symbolic in nature. Or it was a model of neurons that assumed that. Now, which we want to come back to later in our series, of course. But I guess but I believe what you're looking at in trying to determine, and others are too, of course, whether you can find symbolicness in neurons. So many people in the neural net world are trying to make so-called disentangled representations, because there are benefits to having such, it's a human interpretability, but also the ability to chain concepts, and do reasoning correctly. So I just want to say this it's more of a comment, I guess. This thing you're exploring is very deep in the heart kind of neurosymbolic. So I think you were sort of seeming to, wanting to explain why that's relevant to neurosymbolic AI. But I just want to emphasize that I do think it's very fundamental to the issues in neurosymbolic, because roughly speaking, it's, neuro is mostly the viewpoint is distributed representation, symbolic. Mostly the viewpoint is you need a crisp concept, and we are trying to find things that are the best of both worlds, and so this is very foundational, this divide. And so I just want to say, others should be helping Pascal do this kind of research. So very important.
Yeah. So just quickly, so the kind of in the history of neurosymbolic AI, right, pre-boom, the terminology was localist versus distributed representation, and of course there has been a lot going on there. I agree that artificial neural networks take their power probably out of distributed representations, right, rather than very localist. And so when we started looking at that, and others as well, of course, the question was, will we actually find something we can read off, right? And then, it turns out that we do. However, I believe the thing is probably not about finding single neurons, right? It's just where we had to start searching. But, you may find a group firing together that indicates something. And that is kind of, I think, more likely, and that's also the evidence for. If you talk about the grammar types which we looked at in an LLM, right? And then a layer has, don't ask me how many layers the things had we looked at. But then if you can cut that down to 1% of them, then that's still a lot of neurons. But that may already be helpful, right? If you have an indicator, just these whatever 120 together are actually indicating. Now comes noun phrase. Yeah, if we can carry that over to meaning and probably cut it down even further, then that's helpful. So you don't need to go all the way to localist for it to be helpful. So just wanted to say that, and yeah, there's a lot more there, which you could probably do some other time. Thanks a lot for having me.
Okay, all right. Thanks again, Pascal. We'll hopefully be seeing more of him at a future date, and check out his work. And thanks, everyone, and we'll see you next time.
Thank you very much.